Hello and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. NRIS is collaboration between Sigma 2 and the universities of Bergen, Oslo, Tromsø, and NTNU to provide national supercomputing and data storage services. These services are operated by NRIS and coordinated and managed by Sigma 2. In this video, we will show how to schedule jobs on the Betzy Linux cluster using the Math Kernel Library, MKL, for matrix multiplication. Since we already covered the MKL documentation in video 31, we will not repeat it here. Once I signed into Betzy, I was directed to the Login To node. Applying the cd command, we can move to the MKL on Betzy directory that I have created within my work folder. We can list the contents of this directory by executing the ll command. Let's take a look at a Fortran program that employs one Math Kernel Library routine for performing matrix multiplication. We observe that it utilizes a matrix size of 32,768. The MKL routine uses two variables, alpha and beta, as described in the documentation. We guided you through the MKL documentation for this routine in video 31. The matrices are set up with values via an initialization loop, where the OpenMP directive is visible. Note that setting the C matrix to 0 is not needed when using the MKL routine. We set the variables alpha equal to 1 and beta equal to 0 because we are performing a simple matrix multiplication. The MKL routine DGMM is called with inputs, as explained in video 31. We've aligned the naming of the job script with the Fortran program, using an SH extension for the script and an F90 extension for the Fortran program. This convention indicates that the job script is designed to execute the Fortran program. However, this is merely a suggestion, and you can choose any naming convention you like. We can open this job script in the Emacs editor for review. The job script starts by specifying names for the job and the slurm output file. We specify the computational resources required for the job by requesting a single node with a single task. This is because the Fortran program uses a pure multi-threading approach with shared memory for parallel computing, utilizing OpenMP. The Betzy Linux cluster offers 128 CPU cores per node, and we request to use all of these cores for our single task. We set the wall time to 30 minutes, allowing us to wait in the development queue. A production job would usually need a much longer wall time, requiring a wait in the normal queue. In this case, we must remove the quality of service, QoS, option. Regardless of the queue, specifying the account number is necessary. The script variable file holds the name for both the script and the Fortran program, and this variable is utilized later in the script. The advised error handling environment is used. We also need to load the Intel Fortran compiler. Note that we are not using the Intel alias defined in the bash rc file. This is to ensure that our job script does not rely on any specific configurations from the bash rc file in the home directory. It is recommended to use aliases from the bash rc file only at the command prompt, not within job scripts. The Fortran program utilizes OpenMP for parallel computing, so we need to set some OpenMP variables. The number of threads is configured to match the number of CPU cores per task by using a slurm variable that retrieves this number from the computational resources specified in the script. We also apply the OpenMP affinity settings cause and close. The script compiles the Fortran program to ensure it is built on the same type of compute nodes where it will execute. The highly optimized MapMurl routine from the Intel compiler is replaced with the MKL routine. Consequently, we use specific compilation options to link the program with the Math Kernel Library. Note that the backslash simply indicates a continuation of the line, and the complete option for linking MKL is shown in the video with red letters. We use the Intel compiler and the script variable file, which contains the name of the Fortran program. The resulting executable from the compilation process is named mxm.exe. We've added script variables to calculate the compilation duration, and this time is logged in the slurm output file. This measurement is optional, so you can choose whether to include it in your script. The executable is launched on the computational resources specified for the job. The time taken for the parallel computing is recorded using similar script variables, and you can decide whether to include this in your script. The remainder of the job script is as reviewed in video 29. The sbatch command submits the job script to the slurm queue system. The sq command monitors the job status. The job has the specified name and has been active for 11 seconds on the B3366 node. Employing the sq command one more time shows that the job has completed. A slurm output file is generated, but let's first clear the terminal. The ll command reveals that a file ending with txt has been created. However, you can also see that copies of the job script and the Fortran program have not been created, suggesting that the job did not execute successfully. Using the Emacs editor, we can open this slurm file and remember to use the tab key for autocomplete while typing these long file names. The file first indicates when the job started and on which node it was executed. The compilation took about 25 seconds. The compiled Fortran program encountered a segmentation fault, resulting in the job's failure. Let's attempt to fix the segmentation fault issue by making a change in the job script. We will remove the xhost option from the compilation command. We save this change to the file and exit the Emacs editor. We submit the modified job script to the slurm queue system using the sbatch command. We can track the job using the sq command. The job has the specified name and has been active for 10 seconds on the B4149 node. Using the sq command one more time confirms that the job has completed. The job script generates a slurm output file, but let's first clear the terminal. We can verify this by using the ll command, which shows that the file ending with txt has been created. Copies of both the job script and the Fortran program have now been created. You can save these files, along with the slurm output file, to document the versions of the Fortran program and job script used for executing this job. Let us open this slurm file using the Emacs editor and remember to use the tab key for autocomplete while typing these long file names. The file first indicates when the job started and on which node it was executed. The compilation took about 40 seconds, and the execution time was approximately 31 seconds. In our last video, we observed that the execution time using the highly optimized matmul routine from the Intel compiler was around 39 seconds, which is slower than the MKL routine for matrix multiplication. This suggests that the Math Kernel Library performs better than the Intel compiler's highly optimized matmul routine on the Betzy Linux cluster. It's also important to note that the compiler couldn't link and compile the Math Kernel Library when the X-host option was used. The job was submitted from the work folder. The specified computational resources are listed, showing that a single node with a single task using 128 CPU cores was requested. The CPU billing section shows that the billing factor was 128, which matches the number of CPU cores on one node. It also indicates that 242 gigabytes of memory are available on a single node. The job consumed 2.6 CPU hours from the project account. The file shows that the job waited 20 seconds in the queue. Although the requested wall time was 30 minutes, the job had a wall time of 1.2 minutes. The computation was a single task on 128 CPU cores, with a CPU utilization of about 35%. The exit status was 0, indicating the job was successful. The used CPU time was 54.8 CPU minutes, and the unused CPU time was 1.7 CPU hours, resulting in a CPU efficiency of about 35%. The low CPU efficiency occurred because only one core was used during compilation, leaving the other 127 cores idle until the compiled program was executed. The memory usage is reported as 25.3 gigabytes. We can verify the job efficiency with the SF command, which stands for Slurm efficiency. The command shows that the CPU efficiency was about 35%, and the memory usage was approximately 25 gigabytes. Therefore, the SF command confirms the same numbers as those in the Slurm output file. Let's clear the terminal. We can append the output from the CEF command to the Slurm output file by using two greater than signs. Let us check the Slurm output file to see if the CEF output was added. The file shows that the CEF output was appended at the end after the memory statistics. We can open the Fortran program with the Emacs editor and try with a larger matrix dimension. Inside the Fortran program, we'll adjust the matrix dimension to 65, 5, 36. Let's also make some changes to the job script. In the job script, we'll update the job name and the name of the Slurm output file. We submit the job script to the Slurm queue system using the sbatch command. By using the sq command, we can see the status of this job. The job with the specified name has been computing for 12 seconds on the B2338 node. Using the sq command again shows that the job has completed. Let us clear the terminal. The generation of a Slurm output file can be verified using the ll command. Copies of both the job script and the Fortran program have been created, and they can be saved along with the Slurm output file to document which versions of the Fortran program and job script were used for this job. Let us open this Slurm file using the Emacs editor and remember to use the tab key for autocomplete while typing these long file names. The compilation time was approximately 20 seconds, and the execution time was nearly 200 seconds for a matrix dimension of 65, 5, 36. In our last video, we observed that the execution time using the highly optimized matmul routine from the Intel compiler was around 248 seconds. This suggests again that the Math Kernel Library performs better than the Intel compiler's highly optimized matmul routine on the Betzy Linux cluster. The CPU utilization was about 82%. The CPU efficiency has improved because the parallel computing wall time increased to nearly 200 seconds, reducing the ratio of compiling time to executing time. The memory allocation remains at 242 gigabytes, and the memory usage is now around 98 gigabytes. This is expected for a matrix dimension of 65, 5, 36. In our next video, we will examine the efficiency of jobs on the Betzy Linux cluster. I am looking forward to the next video. Wishing you all happy computing in the meantime.